Hello, everybody. Back again. Just got back from being outside. It's rainy and dark and cold out here in New York, and I'm going to make a fun little video. It's more about physical property solution. We're kind of getting through the basic stuff that we can go on to do more things. This chapter really just gets us warmed up for future chapters. We need to know how to deal with solutions, and we deal with them quite a bit in this course, especially when we get to acid-base chemistry in detail, electrochemistry. That's all in solution. So we're going to go over a couple things. It's complementary to the last video on molarity. I'm going to talk about two other concentration systems that are commonly used with solutions. One of them will be a fraction by mass, or you can do a percent by mass. So that's very commonly reported. So we can have, let's say for example, we got 2.00 grams of fructose. Used the sugar before, and we have, let's say we have 100 milliliters of solution we make out of it, out of aqueous phase. It's in water. So we make 100 milliliter solution with this, and let's say at whatever temperature this is, the density is equal to 1.06 grams per milliliter. And let's say we want to get the fraction, the mass fraction of the fructose in that solution, and the percent by mass that's commonly reported. And so the formula is really simple. And so in this case, it will be the mass of the solute, which will be fructose, divided by the mass of the solution, which is an aqueous solution with fructose and water. That would give you a fraction, and you take that and you multiply it by 100 to give you a percentage. We'll just do the percentage first and we'll go backwards. I think people like percentage better. So let's just do it out. So in this case, this is going to be 2 grams of the fructose. And that's going to be, let's say we have 100 milliliters of the solution. And the density is, we want to get mass on the bottom. Let's see, so we have 1 milliliter is 1.06 grams. In this case, we have this, the milliliters will cancel, and we're left with grams over grams, which cancel. We have to have the same units. And so if you want a percentage, that's times 100. That will give me 1.89% fructose. And if we wanted to have the just a fraction, it would be 0.0189, just 2 places. So that could be the other way of reporting it. This is, you're very familiar with the idea of these type of, I just have to get a napkin to wipe the board. I didn't buy an eraser with my board. I just will use kitchen napkins for now. So that should be a very easy concept, but we just use it all the time, so I just want to introduce it. You might use this in labs. This is very commonly used. Mass percentages, and there's other types of percentages. You can do volume percentages and so forth, but for a solution, usually mass percentages are most useful, or mass fractions. So there's another way of reporting concentrations in solution that's very common, and that's called the mole fraction. And they use the Greek letter chi for that. Looks like a nice little X type of symbol, but it's chi technically. You can have this, use this all different ways, but in the context of a solution, let's just take a solution with one solute species and the solvent. You can extend this idea. The big idea is that for the solute, it's going to be the moles of solute divided by the moles of solute plus the moles of solvent. This will give you chi, the mole fraction for the solute, and for the chi for the solvent is similar. Except it's the moles of solvent on the top, and this is just the total moles. So I'll just put total moles here, so you don't have to repeat that. One of the properties, and again, you can do this with more than two components. You could have two solute species that are dissolved in there, and then you would just simply have the moles of solute 1, and then moles of solute 1 plus moles of solute number 2, and then the moles of the solvent, and so forth. One of the properties of this in general is that the sum of the mole fractions equals 1. I'm summing over the index I. So for this, which is just a two-component system with one solute species and solvent, that would mean that the mole fraction chi for the solvent plus chi for the solute equals 1. I will tell you this, a common mistake that people do, that's a good check at the end, but a lot of times a person will calculate, for example, the moles of the solute, and they do it wrong, and then they use this relationship to solve for, let's say, the moles of the solvent, and that's going to be wrong as well. At least if you do both of them independently, then you can check your answer at the end, and it narrows your opportunity for making mistakes on a test or in the lab in real life. And so that's a good tip for that. I would actually do them out. So let's use this. This unto itself is not that interesting, but we're going to use it for things that relate to properties of solutions. Coming up, probably tomorrow, I'll start recording those videos on colligative effects, Raoult's law, and so forth. That are very useful. A lot of them have a lot of relations, a lot of uses, I should say, in environmental science and biology and so forth, including medicine. We'll talk about some of that as we go along. So let's actually work a real problem. I made a problem with two miscible liquids, meaning they mix together in all proportions. I picked methanol, and we have 1 gram of methanol mixed with 1 gram of ethanol. And it doesn't have to be 1 gram, I just kept it simple. I'm going to write out the formulas for this. This is CH3OH, and this is CH2OH. They're similar, just this one makes you drunk and this one makes you go blind. So they have different biological effects in people for sure. And for goodness, let's just calculate out the molar masses. So I got for this and verify this is 32.04 grams per mole. And this species here, the ethanol, is 46.07 grams per mole. And, do not, on the test, this is a skill you have to be very proficient with for doing problems. So don't abnegate those steps from these calculations. Do them out, check my work. Sometimes, I have a tendency to invert numbers. So if you see it's 46.70, don't freak out. I tend to make those type of mistakes in my reading. So let's calculate out. Methanol is commonly abbreviated MEOH, so I'll call it, I don't want to write the whole thing, MEOH, that's the methanol, common abbreviation, it's used in organic chemistry. So, first thing we have to do, I'm stepping a little ahead of myself here, let me erase this, is let's actually calculate the numbers of moles first, that's what I should be doing. So, we have, for example, for the methanol, we've got 1 gram times 1 mole per the molar mass, 32.04 grams, and that gives me 0.03121. I'm just going to write down an extra sig fig here as I'm doing it and round it at the end to 3. On my calculator, when I'm doing this, I just retain all the digits and then I round at the end, but I just don't want to mislead you, because if I limit it early on, you might see a slightly different number than what you're getting. Don't do the numbers out yourself. And what I always suggest is use all the digits on your calculator and then round at the end to the correct number of sig figs. On the exams, I'll just tell you I want a certain number of sig figs, so you don't have to belabor that too much for these problems. because I want you to focus on the chemistry. For the ethanol, I'll abbreviate ETOH, common abbreviation. It's 1 gram, and then we're going to have, for that, 1 mole of ethanol is 46.07 grams. Verify that for yourself. And I got 0.02171, ... keep going. That's how many moles. But I should be writing in here, this is moles of ethanol. So I want to write where it's very clear for you. The let's calculate out the mole fraction for the methanol. For the methanol, you put the moles of the methanol itself. The moles will all cancel, so I'll just leave the units off. The moles of the methanol plus the moles of the ethanol, the solvent. Well, these actually in this case is the who's the solvent really. This is a binary mixture. They're roughly, it's going to be similar volumes. They're not any sort of a big difference. It's really they're mutually mixed together. There's no real solvent or solute here. It's just a binary mixture with two things. It's still forming a solution, but what's the solvent and what's the solute is vague. In these problems. The book, a lot of times, I notice it does this. It'll take water, and it'll always call the water the solvent, even if there's more, let's say, methanol in it. And that doesn't make any sense. It's one of the attributes I don't like about the book, but I did write it, so I can't really complain too much about it. So for this, the 3 sig figs, I got 0.590. Verify that. And for the ethanol, it's similar. ETOH, I'll call it. I'll put it as capitals, how I usually do. Almost off the board with that. So we've got the same number in the bottom, and so you're going to have the 0.03121, the total moles. Got the 1. And then you have the moles for the ethanol, 0.02171. You can tell it's a little bit less. And so for that, I got 0.410. The sum of these together will give you 1. Verifying that property. I've had students come up to me on the test and say it's coming out to be 0.998. It's not 1. You have to take into account that you're working with experimental masses and so forth, and you're having rounding errors. You're not going to get 1.0000. You're going to get something like 0.999 or 1.001 or something like that. You're going to get something realistic, but that's just not understanding the difference between a pure number and these type of numbers that we work with in physical science. So on that note, these are about the length of the videos. I think people like, when I've talked to people about this, people seem to like the idea of shorter videos. Plus, I can upload it in about an hour and a half. It takes me. I'm doing this all on my phone. I'm doing this to the best of my ability in my kitchen in New York. I want to get these videos up before class. If there's anything, they're not going to be. This is not Spielberg. This is not Age of Disclosure. This is Age of Chemistry here. So or Disclosure Day, I guess is the movie. This is Chemistry Day. If there are significant problems, like you can't read it or something like that, you want me to write bigger, let me know. But I'm not going to do any kind of fancy productions. There's going to be no confetti falling out of the sky or banners or anything like that on this. I just want to make sure we can do the calculations. So we'll continue on with more videos tomorrow or so. We're going to probably get pretty close to wrapping up this chapter. As I'm uploading this, there's a few people I can tell watching these videos before the semester starts, and that's great. If you do catch 1 or 2 of these videos, and if you're not taking classes right now, I don't know your work schedule, I would be studying, because this is going to be a really quick semester, and I would focus on getting ahead a little bit. Well, on that note, I'll let you go, and have a great day or a great night. Take care.